Welcome back. This is Module 13, Building Microservices and Serverless Architectures. In this module, we will look to the architectural need, introducing microservices, and building microservice applications with AWS Container Services. Frank and Martha want to get daily reports via email about all the orders that were placed on the website. Frank wants to anticipate the demand so he can bake the correct number of desserts going forward. Martha wants to identify any patterns in the cafe business. Currently, Sophia has set up a cron job on the web server instance that sends these daily reports, emails, messages to Frank and Martha. However, those jobs is resource intensive and reduces web server performance. Olivia advises Sophia and Nickel that non-business critical reporting tasks should be kept separate. Sophia and Nickel want to further decouple the architecture and move the cron job into a managed serverless environment that will scale well and reduce costs. So will introduce us to microservices. So what are microservices? Microservices are an architectural and organizational approach to software development where applications are composed of independent services that communicate over well-defined application API. This approach is designed to speed up deployment cycle, and the microservices approach fosters innovation and ownership and improves the maintainability and scalability of software applications. To understand the benefits of microservices, consider first a monolithic application, a legacy application. In this example on the left, the three processes, users, topics, and messages of a monolithic forum application where user can make a post and also user can reply to a post in a specific multi-threaded forum. They will reply with comments. You will see that this monolithic forum application, all components are tightly coupled. They run as a single service. If one of the processes, let's say the messages of that application experiences a spike in demand, the entire architecture must be scaled as well. Adding or improving features to one of those topics very complex because you have to maintain the whole code for all services altogether, which limits experimentation and makes it difficult to implement a new ideas. The availability of monolithic application is also at risk because many dependent and tightly coupled processes increase the impact of a single process failure. Suppose that the same application runs in a microservice architecture. Each process of the application is built as an independent component that runs as a service. The services communicates by using a lightweight API operation. Each service performs a single function that can support multiple applications. Because the services run independently, they can be updated, deployed, and scaled to meet the demand for a specific functions of an application. A microservice architecture provides much a quicker iteration, automation, and overall agility where you can start fast, fail fast, and recover fast. Now, what are the characteristics of a microservice? Microservices share some common characteristics. They are decentralized. Microservice architectures are distributed systems with a decentralized data management. They don't rely on a unifying scheme in a central database. Each microservice has its own view about data model. Microservices are also decentralized in the way they are developed, deployed, managed, and operated. Microservices are independent. Each component service in a microservice architecture can be changed, upgraded, or replaced independently without changing the functionality of other services or other components. Services do not need to share any of their code or implementation with other services. In a similar way, the team responsible for different microservices can act independently from each other. Microservices are specialized. Each component service is designed for a set of capabilities and focusing on a specific domain. If the code for a particular component service reaches a certain level of complexity, then the service can be split into two or more services. They are polyglot. Microservices do not follow a single approach. Teams have the freedom to choose the best tool for their specific problem. As a consequence of this, microservices architectures take a heterogeneous approach to the operating system, programming language, data store, and tool. This approach is called polyglot persistence and programming. Microservices are black boxes. They are not a white component, which means we deal with the box or with that component out of the box without revealing the content of the box. Individual component services are designed as black boxes, which means that the details of their complexity are hidden from other components. Any communication normally happened between those services happened through a well-defined API to prevent implicit and hidden dependencies. In summary, microservices, you build it, you run it, and it is a key organizational principle for microservices to use the DevOps, where the team responsible for building a service is also responsible for operating and maintaining it in a production. So let us look how we can building a microservice application with AWS Container Service. Now, before we understand that, let us understand what we mean by a container. And to understand this, let us take two examples. We will take Docker, which is the containerization service that we have currently. And we will have, for example, WordPress. And we will look to both the WordPress installation, and this is normally for people who are not familiar with microservices and how and why we need them. So if you look here and you want to go to the WordPress installation guide, this is how to install WordPress, for example. Installing WordPress, you need to choose multiple things. You can install it in a popular hosting or a standalone, and you can look, for example, into those. So you have like installing WordPress in DigitalOcean, for example, and you will come to this guide, which normally will take you a few hours to do this. So you have to download WordPress, you have to install all the pre-configuration, you have to mount all of this, and then at the last page, you need to run WordPress successfully in order to manage its component, maybe configuration, and link it to your database. And instead of dealing with WordPress as a standalone service, we can deal with it as a service via a very famous tool. We call it Docker. Docker engine, guys, is an engine that you can use to build and to run a microservice. So you can read more about docker.com here, and you can do the tutorials here if you want to understand more about containers. But most importantly now, you can get a start with Docker, or you can just go to Docker Hub, which is the container repository where you will find multiple containers available to you. Most importantly, what I want to show you in this demo to understand microservice, that you can look for a WordPress Docker container. So let us look to WordPress Docker container or Docker image, and you will find that in Docker Hub, you can use and download and run WordPress using this command. So if you put in your terminal, docker pull WordPress, this will download Docker into your machine, and you can also run it as well. And you can specify how you want to run it, for example, at port 8080. So let me copy this simple command, open terminal, and this is for you guys just to understand what we mean by a Docker container. Now, before I will run the command, go back to this installation guide and look how to install WordPress in Ubuntu 14.04. That was modified in 2014. And this is the guideline. You have to do the prerequisite, create MySQL server, download it, configure, and it will take you so much time. And most of the time, you will find here a missing dependency or some libraries that you want to overcome those issues until you manage to do it. With Docker, if I paste this command, I will be able now to run Docker container in no time. So with Docker now, all I need to do is just to put this command, and will pull the Docker image from the repository. Remember, Docker Hub is a public repository, and we will understand a similar service to it in AWS now. And you will be able to see that this Docker image now it is running. If I go to something called Docker dashboard, I could check this from my CLS. So I could do a command like this, but I don't want to show you this. I want to show you the dashboard of Docker, which is the graphical user interface, much easier because you just want to understand what a container is. So if you look to the dashboard of Docker, you can see there is a WordPress. There is multiple images also I use for building and testing. And you will find that there is a container called WordPress running now in my computer. If you look to the guideline here, when I pull the image, Docker pull, will pull the WordPress image. And this command here, docker run, is going to run that image. So I am supposed now to see the WordPress installation at port 8080. So let me just do that. If I go to http:/localhost, because it's running locally in my computer at port 8080, I most likely will see the full installation of the WordPress ready out of the box. And this is what we mean by container. So let us now continue. What is a container? When you build a microservice architecture, you can use containers for the processing power. Containers are a method of operating system virtualization that enables you to run an application and its dependencies in a resource-isolated process. A container is a lightweight, standalone software package. It contains everything that a software application needs to run, such as the application code, runtime engine, system tools, system libraries, and configuration. Containers can help ensuring that the application deploy quickly, reliably, consistently, regardless of a deployment environment. Containers also give you more granular control over resources, which improves the efficiency of your application. A container is created from a read-only template that is called an image, and this is what I just showed you in the WordPress demo. Images are typically built from a Docker file, which is a plain text file that specifies all the components that are included in that container. You can create an image from scratch, or you can use images that others created and published to a public or a private container registry similar to Docker Hub. A container image is the snapshot of the file system that is available to the container. For example, you might have the Debian operating system as a container image. When you run this container, a Debian operating system is available to it. You can also package all your code dependencies in the container image and use it as your code artifact. Container images are stored in a registry. You can download the images from the registry and run them on your cluster. Registries can exist in or outside your AWS infrastructure or inside the AWS infrastructure. So how you can run containerized application in AWS? You can use Amazon Elastic Container Service. Amazon Elastic Container Service is a highly scalable, high-performance container management service. It supports Docker containers and enables you to easily run applications on a managed cluster of Amazon Elastic Compute Cloud instances. Amazon Elastic Container Service is a scalable cluster service for hosting containers that can scale up to thousands of Docker containers in seconds, monitors container deployment, manages the states of the cluster that runs the containers, schedules containers by using a built-in scheduler or a third-party scheduler. Also, Amazon Elastic Container Service is extensible by using API, so anybody can extend it by that API call. Can be launched with either AWS Fargate or Amazon EC2. And let us understand now the difference between those two orchestration in AWS. So that Amazon Elastic Container Service is a regional service that simplifies running application containers in a highly available manner across multiple AWS availability zone within a single region. You can create an ECS cluster in a new or existing virtual private cloud. A cluster is a logical grouping of resources in AWS. After a cluster is up and running, you can define tasks, and those task definitions will be running as a service in your cluster. Normally, the task definition and services that you specify refer to a Docker container image to run across your cluster. A task definition is a text file in a JSON format. It describes one or more containers up to a maximum of 10. That from your application. You can think of it as a blueprint for your application. Task definitions specify parameters of your application, for example, which containers and launch type to use. Other parameters include which ports should be open for your application and which data volumes should be used with the containers in the task. A service enables you to specify how many copies of your task definition to run and maintain in a cluster. You can optionally use an Elastic load balancer to distribute the incoming traffic to containers in your services. Amazon Elastic Container Service maintains that number of tasks and coordinates task scheduling with the load balancer. After you create a task definition for your application, you can specify the number of tasks that will run in your cluster. A task is the initial of the task definition within a cluster. When you use Amazon Elastic Container Service to run tasks, you place them in a cluster. So a task is the instantiation of a task definition within a cluster. So a task definition is the source code of the task, and the task is that source code at runtime. Finally, Amazon Elastic Container Service downloads your container image from a registry that you specify and runs those images within your cluster. Now, the option offered by AWS are Fargate or EC2s. So Amazon Elastic Container Service offers two launch types for hosting your containerized applications. You can use the Fargate launch type to host your cluster on a serverless infrastructure that Amazon ECS manages. You only need to package your application in containers, specify the CPU and memory requirements, defining networking and AWS identity and access management policies, and launch the application. If you want more control, you can use the EC2 launch type to host your task on a cluster of an EC2 container instances that you manage. A container instance is an EC2 instance that is running the Amazon ECS container agent. You can use Amazon ECS to schedule the placement of containers across your cluster based on your resource needs, isolation policies, and the availability requirements. Amazon Elastic Container Service keeps a track of all the CPU, memory, and other resources in your cluster, and it also defines the best server for a container to run on based on your specified resources requirements. You could also create an auto-scaling group for your Amazon ECS cluster. The auto-scaling group contains container instances that you can scale out and in by using the Amazon CloudWatch alarm. If you configure your auto-scaling group to remove container instances, any tasks that are running on the remote container instances are stopped. And this is very important, guys. If your tasks are running as part of a service, the Amazon Elastic Container Service restarts those tasks on another instance if the required resources are available. You can have an example of such required resources, including CPU, memory, port. However, tasks that were started manually are not restarted automatically. You could also take an advantage of Amazon Elastic Container Auto Scaling, which gives you more control over how you scale tasks in a cluster. It increases the speed and reliability of a cluster scale out and gives you control over the amount of spare capacity that is maintained in your cluster and automatically manages instances termination on a scale in. When a cluster auto-scaling, you can configure Amazon ECS to scale your auto-scaling group in and out automatically. With a cluster auto-scaling, relies on capacity providers, which link your ECS cluster to the auto-scaling groups that you want to use. Each auto-scaling group is associated with a capacity provider, and each capacity provider has only one auto-scaling group. However, many capacity providers can be associated with one Elastic Container Service cluster. To scale the entire cluster automatically, each capacity provider manages the scaling of its associated auto-scaling group. So how now you can decompose a monolithic application and you change it to microservice architecture. So in the first step, you can have those monolithic volume application you studied earlier where the entire application runs as a single service. To re-architect this application by using microservice architecture, you can run each application process as a separate service within its own container. With a microservice architecture, the service can scale and be updated independently of the others. To deploy the monolithic application as a microservice application, first, you need to build and tag an image for each service in separate from the other. Then register the images with Amazon Elastic Container Registry or Amazon ECR. In step 2, you need to choose a launch type and create a new service for each piece of the original monolithic application. Amazon ECS deploys each service into its own container across an Elastic Container Service cluster. Then you need to create a target group for each service. The target group tracks the instances and ports of each container that is running for that service. In step 3, create an application load balancer and configure a listener rules to connect to the service. The listener checks for incoming connection requests to your load balancer and uses the rules to route traffic in an appropriate way. In the example, the listener for the application load balancer listening for the HTTP service request on port 80 and routes them to the appropriate services like /API/users or /API/topics. Each one of them, they will be routed into a target group. There is a few tools that you can use to build highly available microservices architecture. AWS Cloud Map and AWS AppMesh are two tools that can help you build highly available microservice architectures. AWS Cloud Map is a fully managed discovery service for cloud resources. You can use it to define custom names for your application resources such as database, queues, microservices, and other cloud resources. AWS Cloud Map maintains the updated location of these dynamically changing resources. This location maintenance increases the availability of your application because your web services always discovers the most up-to-date locations of its resources. You can add and register any resource with a minimal manual intervention of mapping. AWS Cloud Map assists with service discovery, continuous integration, and health monitoring of your microservices and application. When you create your task definition, you could enable app mesh integration. So what is app mesh integration? AWS App Mesh captures metrics, logs, and traces from all of your microservices. You can export these data to Amazon CloudWatch or AWS X-Ray and compatible AWS partner network and community tool for monitoring and tracing. AWS App Mesh also enables you to control how traffic flows between your microservices to make sure that every service is highly available during deployment, after failures, and as your application scales. AppMesh enables you to configure microservices to connect directly to each other via a proxy instead of requiring code within the application or by using a load balancer. AppMesh uses Envoy, an open source service mesh proxy, which is deployed alongside your microservice containers. And finally, Fargate. So we have learned that Amazon Elastic Container Service offers two launch types, Elastic EC2 instances and Fargate. So what is AWS Fargate? And this is, I believe, very important for the exam. AWS Fargate is a fully managed container service that works with both Amazon Elastic Container Service and Amazon Elastic Kubernetes Service. It enables you to run containers without needing to manage servers or a cluster. With AWS Fargate, you no longer need to provision, configure, and scale clusters of virtual machines. With AWS Fargate, you no longer need to provision, configure, and scale clusters of virtual machine to run containers. As a result, you don't need to choose server types, decide when to scale your clusters, or optimize the cluster packing. AWS Fargate reduces the need for you to interact with or think about servers or a cluster. Fargate enables you to focus on designing and building your application instead of managing the infrastructure that runs them. And let us look now to the first guided lab, breaking a monolithic Node.js application into microservices, which is an optional demo that you could look if you are interested to study serverless and microservices architecture. We'll prepare in this lab Cloud9 dev environment. We will run a monolithic application written in Node.js, containerize the monolithic for Amazon Elastic Container Service, and then we will deploy it to Amazon Elastic Container Service and refactor the monolithic into containerized microservices. It is a very important lab for the guys who are interested to get more insight, hands-on on the technical and microservices. So this is the final product of your lab. You will use Elastic Load Balancer to point to different service endpoint, and that different service endpoint will be running on Elastic Container Service cluster. The estimated time for this lab is 3 hours.